Welcome to applications. This is the first turnaround for applications. This has got important implications for your exam, so it's one not to neglect these applications videos this week. Alright, so many problems from various practical situations requires the use of differentiation, and applied maximum minimum problems might be called optimisation. That is to optimise the material being used or whatever it is that's needed, time, gas, matter. We may need to find the maximum minimum value for a function. Right, a rectangular paddock is to be built from 80 metres of wire, so that's the first thing that we notice, a rectangular, and that means that the perimeter is 80 metres. How should it be built is if it's to have a maximum possible area. So there's a distractor in the question, but I'll leave that for the moment. So we'll just do a little rectangular paddock, and we'll suggest that we'll let the length and the width, because they're the way we would normally do it, but one of the things that I've made an emphasis about in the workshop videos is that we need to have things in terms of a function, okay? So let's call the width y, and let's call the length x, okay? So at this point in time, we're not sure anything about this other than that we know there's two y's and two x's. So we can put together a perimeter equation. Okay, so perimeter would normally be two lots of the width plus two lots of the length. So we're moving away a little bit from that basic geometry idea so that we are considering our function type ideas. So we've got 80, so let's put the 80 on the other side. Well, we've got 2x plus 2y is equal to 80. That was information given in the question. Okay, so Maths 1's got a lot of these in them, these types of questions, so it's good to get a bit of a hang of it now. The other thing that we know in common geometry, in the question it asks for the area, so the area would normally be the length times the width, but we need our area to be x times y. Now, we're very close to doing what we need to do, and we've got our kind of stage 5, year 8, 9, 10 geometries, but we need to move it into calculus. What do we need for calculus? We need calculus to be a function. At the moment, a is a function of length and width, or x and y, so we need to convert that into a single function that we can operate on. Okay? So what we want to do is combine these two equations and use them together. Okay? So one more step we can do here is to divide by 2. So everything would get a 2, everything would get a 2, and everything would get a 2. And so this would become x plus y is equal to 80. Now we're putting in that very maths sense, that very mathsy sense, okay? And the other one that we've got, now I've made a plus of that, it should be times y. So the other thing we want is xy is equal to area. So what we can do is we can take one of the variables, y for example, and make it the subject. So we just subtract x, and so we get y equals, in terms of parameter, 80 minus x. So then we take that and we substitute that in to our equation. So what we're going to get is a new relationship. We're going to get a in terms of x, and we'll put a bracket in because we're going to times this. We don't want to break the algebra. So we put a bracket in, and we've got a new function. So that's minus x, so doing the expansion, it's minus x squared plus 80x. Now we'll notice that everything in here is just in terms of x. There's no y, there's no kind of year 10 geometry. What we've created is a function in terms of x. So that's always the big deal. When you're using calculus, we've got to convert the things that we know, basic kind of geometries, and we've got to convert them into a function that we can use in calculus. So this becomes a function of x. So in a nutshell, that's our first big step. Our first big step was to reconcile all of the simple geometry into the area as a function of x. Now the thing was we had to maximize this. So what we want to do is, now what you'll recognize, of course, is that this is an upside down smiley face, isn't it? Not sure exactly what it looks like, not sure where to put the y and x, but this is minus x squared, and the 80x is going to shift it off somewhere. So before we get to all of that, you could complete the square and sketch that if you wanted to, but we don't need to. We just need to go ahead and do our derivative. So our derivative is going to be a dash of x, a dash of x, or a prime of x. So the 2 will come down the front, and the 2 will become 1, so I won't even write the 1 above the x there, minus 2x, and the x will disappear, and we will get a derivative of 80. So our main task in doing all of our max mins is that we assign the derivative to 0. That's our big deal, isn't it? Okay, that's the one that we're here for. So that means we've got to write it as solve, the way that we would normally do. So we're and what does this tell us? What does this tell us? This tells us the x value. It's not the solution of the quadratic, that would be up here. It's the solution, which would be the x-intercepts. It's not doing that. It's doing this. It's finding this bit. Where's that bit? M equals 0. Where's the x value? Where's that x value? So we're going to solve this. So I can just maybe add 2x to both sides, just to keep it simple. So 2x is it, and just swap it around because it's not an inequality or anything. I don't have to change anything. Okay, dividing by 2. And so we get x is equal to 40. So what did I do there? I didn't pay attention, I was talking too much. I wish I did do that sometimes. How about I did it all in my head, you see? Writing it out. So we've got 2x is equal to now what did I divide by 2 up here? If I divide it by 2 up here, I get x plus y equals, see that mistake there? That's 40. 40. Keep doing that, don't I? 40. Goodness gracious, I've put it everywhere. Okay, 40. 40. Once you do it, it sticks, doesn't it? You've got to make sure you do the right thing. 40 is divided by 2, you see? That's the divide by 2. 40. So we put the 40 in. Assigning that all to 0. And 40. So 2x is equal to 40. That's a bit better, isn't it? So dividing by 2 again. And so x will be equal to 20. So that value is 20. X. At 20, we get our maximum value. We find our maximum value. Now, if we go back to the original function, the undifferentiated function, and put that 20 in, we will find our height. So minus 20 squared, put the bracket in because the minus is not part of that squaring, and so we'll get plus 40 times 20. And the easiest thing to do would be to take the naught off and put it back on. But 20 squared is 400. And 40 times 20 is 800. And so what we get is minus 400 plus 800, which is a height of 400. So our y value is equal to 400. That's the coordinate. So this coordinate is 20, 400. That's where m is 0. M is 0. So we've made our m equals 0. All right, so now that we've got the location of our particular problem, what is its nature? So we can do the second derivative test. That is, we can do a double prime x. So minus 2x plus 40 is going to become minus 2 on differentiation. Okay, so differentiating this a second time. Now what do we notice here? Minus. That means it's concave down, which is correct. Okay. Alright, so let's just check. If x is 20, the area is 400. Now what we haven't worked out is y. We need to work out what, we worked out the area. Okay, this is the area. So this is where it can be confusing. This is the area graph of a of x, which is the y value, but that's not the y of the assigned variables. Oh, that's not x plus y equals 40. So we better resolve that. X plus y equals 40. That was what we introduced. We could have left it as w and l. Maybe that would have been wiser. Maybe. And we worked out that x was 20. So 20 plus y is equal to 40. So if we subtract 20 from both sides, then our y in the perimeter will be 20. So we've got an xy pair of the variables of 20. So we just need to be mindful of that. If we go and reassign x and y, we might get ourselves a little bit mixed up. Okay, because if we're not dealing, as soon as I made that y there, because this is an xy axis, this graph, as soon as that's an x and that's a y, you see? So we're talking about the function, but that's not the problem x and y. So we need to just be mindful of that. All right, so it turns out for our length and width, which I probably length and width answer the question. The paddock it's been just now at the opening part I said there was a bit of a distractor, and the distractor is that the words were rectangle. Now, in order for the maximum area to be obtained, the we must have x and y at the same length. So that makes it a square. And a square is a subset of a rectangle. It's a rectangle with the same length. Obtain maximum possible area. And it didn't say to state what it is. It just wanted x and y. Not the graph x and y, but the length and the width. So yeah, so maybe changing x and y, maybe just stick to your old geometry. Because once you bring in your function of x ID, the graph, there's a function, this has a graph, doesn't it? A of x has a graph. It has a graph y. So we just need to be careful of that. Paddock must be 20 by 20 to obtain maximum possible area, which happens to be 400 meters squared. Okay, so that's not the answer. This is the answer. square. Wow, who knew? All right, so just be a little mindful of that. And what I might do, I've changed this to x and y. Look, it's not much for me, really, to just run this through again in the variables L and W. And I'm going to do that just to show you what I'm worried about for you. If we've got a length and a width, and we know that 80, which is the amount of y we have, is 2 lengths plus 2 widths, and we can divide by 2, and so all of that would be a length plus a width is equal to 40. We also know that area is equal to length times width, and that's the function that we want, but it's no good having it in terms of one variable. So we can take the area as a function of length, and so length would be equal to 40 minus the width, or actually we'll make it width is equal to 40 minus the length. So whichever choice you make here is important. 40 minus the length, because that's the thing that's going to get substituted in, and then we'll have an area function which is equal to length times 40 minus L. Okay, now we just want to be careful here because we're going to make this minus L squared plus 40L, and now we've got this area in terms of L. Okay, area in terms of L. So we would just have that there. Now, over here, if we were to draw this on a graph, what would we have along the bottom? Instead of having x, we would have L. And our area would be a function of L. Okay? That's the equivalent of having y and x. That's how we would normally present them on a graph. Okay? So it's just that little distinction that I made by not having x and y, because if you don't get that substitution right here, you'll end up having y instead of x. It could be getting a little bit fraud. Alright, so A dash again, nothing else changes here. It's just as we did before. So minus 2L plus 40, and solve. And so we just sign that minus 2L plus 40 is equal to 0. So I'm adding 2L to both sides. And so we get 2L is equal to 40. Divide by 2 both sides. So our length is equal to 20. Okay, so by solving the derivative, the length value at 20, somewhere on there, represents the maximum. Okay, now to get that, we would need to put this in and put our 20 in, and we would have minus 20 squared plus 40 times 20. Just not writing sometimes. So 20 squared is 400, so minus 400 plus 800 is the area. Okay, so that's plus 400. So that's the value of the function at x equals 20. So that's 400. That's the area as a function of L. So we know that that point is 2400, and 2400 is just the place where you get m equals 0. Now, that's not the length, that's not the width, that's the area function. Okay, so to get the width, we've got to go back up here and solve this. Okay, so we take the width problem away. Our length was 20. plus width is equal to 40, and whether you solve that or just observe that 20 more is 20, W is equal to 20. Okay, so that's the maths idea behind the answer. W is equal to 20, so we get a square with a maximum area. We denote a square by marking all the sides, and it's a 20 side with a 400 area. Okay, so however you use your pronumerals, that's important. Now, in terms of the maximum idea, we want to just check the second derivative. Okay, so a double dash of L is equal to minus 2. So what we can see is that that is a big minus, which means it's an upside down. And we know that. We know that anyway because we saw the original quadratic. All right, so we could solve the problem for the crossover. It doesn't say sketch the graph in the question, but I just wanted to redo that to help you to be sure that you know whether or not you're doing the algebraic part or you're doing the calculus part. Which part are you doing? And the choice of pronumerals and the use of your substitution bear quite heavily in that. Okay, so if you're getting flummoxed or confused when you're doing your work, just go back and check which pronumerals you're using and then how you're using them in here. Because if you put, what I did earlier was I put something like L equals 40 minus W, well, then I'd be having a function in terms of width. And that's okay. There's nothing wrong with that. So it's just the convention of the previous example was trying to get the convention to be in terms of X, but that's not important. Okay, it doesn't matter which pronumeral we use, the maths is the same. All right, so I'll pause there on that one, and I'll come back and have a go at this one. See you soon.